I think startups and companies, they do quantum computing, they might say, oh yeah, this is look like our lab. Yes, it is, because the refrigerator is there, and then people standing, smiling, and so on. Yeah, it looks less messy, right? But usually it's much worse than that. Why research in quantum computing, and which direction we go? Of course, if you have read something also about the past, 5 years ago, 10 years ago, Intel also has announced a quantum chip based on superconducting, 49 qubits. It was like 6 years ago, in collaboration with the Delft University. But we have realized one thing. For producing this chip, we didn't use our key advantage. That is our silicon manufacture process. So what we have decided recently I mean like 3-5 years ago, to say, okay, maybe we can use our manufacture line. This gives a key advantage. First, we can produce as many chips as we want. Second, the researchers are there. If something goes wrong, they can go and produce an additional chip. So we have the advantage to produce hundreds of chips and test it. Those are based on silicon, and this use the same manufacture line that we use for our HPC. Of course, this is a dedicated line for high-performance computing, for quantum computing, sorry, but it's very close. And we use all the knowledge that we are acquired in 15 years in silicon. Now, demonstrating that the chip that we are producing, that is actually this one, is working or not, this is another thing. What I can tell you is that with our manufacture line on the same die, that is a 300 millimeter die, we can have a lot of those chips. The problem is that how reliable is the chip? How fast is the chip? What is the noise? All the same problem here. But without this technology, you can forget about everything about quantum computing, because without hardware, everything you are building on top is just nice. It's just learning how to optimize code. But without without the hardware running, then maybe it's not good. Yeah, this is what we produce. This is what is called spin qubit. So, who knows about spin qubits? Okay. So those spin qubits, so now the question is, where do we encode the quantum information? So of course you have to use a 2-level system. I think if you know the loss, Di Vincenzo, and hardware and so on, you have to use a 2-level state. In this case, use a single electron and use the spin of the electron, the magnetic moment of the electron. The thing is, okay, how to manipulate it? You have to manipulate a single electron. You have to think how hard is that. So a single electron encode a single qubit. What they do here is with an external pulses, they create this well. It's called quantum well, and actually it's a quantum dots. Inside this quantum dot, they can trap electrons, and each electron encode 1 qubit. Okay? This is the way, on high level, how we manufacture the chip. And the latest chip we have is Intel Quantum quantum dot chip. This is a 12 qubit chip that we have produced. So this is a nice chip. There is also some fidelity issue, but this is what we are able to manufacture. What we do here, when you in the manufacture line, as I said, right, there is a die of 300 millimeters, and then you can produce several of these quantum dots. Means that you can then packaging several of these spin qubits. But then, what is the problem here? It's always I'm trying to explain you how difficult is the technology, because actually each chip is going to this cryostat. If you produce 100 chips and you want to test all of them, do you have 100 cryostats? You know how much expensive is that? You don't. Maybe you have 3. This is the picture. You have 3. Actually, we have a bit more than 3, but it's around tens. This doesn't scale. It means that even if we have the potential to produce 100 of these chips, testing those chips is a challenge. And I think it's a challenge for all the hardware companies. So this is an issue. So anyway, we can produce a reasonable chip that can be tested and where we can run our application. what do we do here? So, of course, you can say, okay, but you are producing in 12 qubits, it's not very large. Yeah, of course, at the moment we have 12 qubits, but this is not what we think. Everything we develop, we have in mind those numbers, billion qubits, because we want to produce a commercial state quantum hardware. 50 qubits and around 100 qubits is a nice device to have, but always is for proof of concept and learning and research. We do that. We collaborate with academia, we collaborate with the research. It's for learning how quantum computing works, but it's not for producing any meaningful results. The results is just noisy, the results is not reliable, but this is the way to learn, and this is a good learning process. The quantum hardware, as was explained also in the other talk, is also seen as an accelerator for classical HPC. That's why HPC institutes, they try to understand how to integrate quantum hardware in the HPC. So this is a kind of quantum HPC integration. So this is the way we envision regarding the quantum computing development. But there is an additional piece I forgot to mention. Okay, you can use your manufacturer line, so we can use our manufacturer line, we can have spin qubits. Then you have the cryostat, you have to put everything in the cryostat, but you have to send the signal to this circuit. How do you send it? I mean, you have to send these pulses, how do you change it? Yeah, of course, there is an external device, but then you can send the pulses. This external device is connected with cable inside the cryostatic chamber, but this might not scale. If we think about 1,000 qubits, 10,000 qubits, 100 qubits, how many cables you have to have there? I mean, it's not feasible. That's why we have another branch of research that is not only producing the chip, but it's producing what we call control electronics. This is a chip called Horsefish. This you have to think like a sort of multiplexing device. Actually, a key advantage is also working in the cryostat with very low temperature. So in this case, this will address the Horsefish control chip, will go and will address directly the chip with less number of cable connections. This could give an advantage. That's why we develop a full stack quantum computing. And I'm talking all about the hardware. Of course, I will not miss the software part. That is the part that is related to the conference. But I want to tell you that we can talk about the software, hours, days, but without this piece of technology, this is just nice to have, but it might not work. So just is the way we see that. Good. On top of the control qubits, then you have to build something that runs. And we know our technology. We know how to build it, which compiler to build and runtime. So the two pieces that are missing are the quantum runtime and the quantum compiler. Everything that you see on the right part, quantum dot simulator, qubit control simulator, and quantum compiler runtime, those are pieces of software that we use to test our hardware. So what do we do? Of course, producing the spin qubits might take time, but you still can simulate. How you simulate? Okay, you have a quantum dot simulator. Then there is a pulse that you give the pulse you have to give, the signal. Then how do you do that? Before waiting for the right hardware, you can simulate. And the same for algorithms. So you have to write your algorithms and you have the compiler runtime instructions, all the steps. We have put everything in the software at the moment. So what I'm saying is that the MITAD, if you remember, is full quantum computing in simulation. This is what we meant. So in our research lab, we don't only do the hardware, the left part, but we do also the right part. The good thing is why we are doing that. Building a device, it could be a quantum device or it could be a classical device. You have to have a fast feedback with the manufacturer line. If something goes wrong because your algorithm doesn't work, then you have to give the feedback and they have to change something there. So we do the same. We use the same approach of co-designing the quantum hardware with the quantum software. And those are all the 6 components, the main 6 components that we have control of. So starting from the qubit, control electronics, the process, and so on, and application algorithms. The question also could arise, okay, but which kind of application algorithm you are going to test to give feedback to the quantum hardware? This is a big question. we have a certain standard benchmarks. I think it's also known here by other talks, what kind of benchmark to use, what kind of a problem to have, but it's a standard benchmarking process that we do. The nice thing of that I don't want to miss, that this part of the software is provided now for developers to test. It's provided for free, and you can download and use it. Right now, so we have the what is called Intel Quantum SDK that you can download. I will show you the links and so on, and you can start using. The stack is composed by all these components I mentioned to you. There is the simulation environment, there is the runtime environment, the application development. And there are two ways, if you see two columns here, generic qubits and the Intel hardware. So you can even use the Quantum SDK, Intel Quantum SDK, to simulate a generic qubit. Like it could be anything. You can even give also configuration. Say, okay, this is the noise in my qubit, and I can simulate it with your environment. Or you can use the models that we use for our silicon. So the qubit control simulator and quantum dot is also provided. For simulators, we have the most common technique, tensor network and state network. I think you might know. And so this is the software that we provide. We have also made some design choice that I'm going to show you that we think might be important to ease the integration of the quantum development with HPC, the current state of art of HPC. And we have chosen one thing. So from our experience of high performance computing, we know that, I mean, it was mentioned, the most used classical languages are Fortran and C++. So I've been to the doctor yesterday that also C could be also an option. We have chosen C++. And the reason is that there are several reasons. Of course, those are the things we have mentioned, like we have extension for the language, we could write parameterized circuit, but despite all the technology here, there is a main reason. First, there is, so we would address, the market that would be addressed at the beginning is a high-performance computing. In the high-performance computing environment, C++ is becoming more popular than Fortran. Said, okay, let's start with C++. The transition might be very easy. Second, you can use standard C++ libraries that could be embedded to build your hybrid program. And the third part is that we have experience for other software development, like, I don't know if you heard the Intel compiler, the One API, and so on. We bring this knowledge also to this technology. That's why we have chosen the LLVM-based compilation. So we have extended the language with some data type and some kernel-based, and we use the compiler, LLVM. So we developed extension to LLVM to allow C++ quantum program. On a highlight, what we have, so we have quantum-specific intrinsics, so extension. So if you have your code, I will show you also code here, very simple code later. But there are quantum-specific extensions. And of course, once you compile, this is not all the job. So there is runtime. You have to run your binary. Which runtime you use? The runtime actually, since you are, so the quantum hardware is still not available. Okay, you cannot run this on the speed on the spin qubits. But we are developing the runtime that is the same that we use for this feedback loop of hardware development. So the quantum runtime provided is the same. The only thing it changes is the backend. At the moment, the backend is on simulation. So you can simulate. So the quantum runtime, we choose the simulator that you have set. So it could be the state vector, tensor network, and so on. Indeed, here is a part of configuration. So you see you configure, for example, noiseless or noise simulation, the full state simulator, and you give some parameter, and then will be run. The programming model is a kernel-based programming. Means that if you are familiar with GPU programming, you write the kernel, this kernel will be offloaded to a machine. This is a similar thing. So it will be very familiar for HPC people. We are trying to address such problem. It's not an easy thing. I think there are other frameworks in Python. We provide also a panel interface, but if you really are starting for quantum computing and you want to learn, I think this is you have to put a bit more effort to understand. Because it's based on C++. If you want to know how Hadamard gate works, I mean, I would not recommend doing that. Just use any Python framework that you find online. That's much better. This is really for thinking about integration and doing HPC. For more technical folks here is that, okay, I talk about compiler. I mean, this is the key driver. This is the key driver of the component that we provided to researcher for free. But you see here, I mean, it's just a short list of the steps that compiler is taking to generate the code that we run at the moment on the simulated environment, and we run also on the quantum hardware. So you see, I mean, starting from bottom, you might have even compiling and linking. This is what we are doing here. It's one question is, am I linking also classical library or not? So I mean, you could write a code. If thinking about HPC, thinking that the quantum hardware is there, do I want to link? Can I link BLAS, LAPAC, MPI? I mean, this is something that we are building on top of compiler. So it means that you could link generic library, classical library. Then going on top, for example, okay, the C++ is written as a classical programming language. You are mixed up with quantum. And then if the compiler does optimization, should I do classical optimization or not? Loop unrolling, I mean, it's the easiest one. So those are important questions, and we try to address why we developed the quantum compiler. The classical part will remain, we do the loop unrolling, but when the classical part interact with the quantum part, then it's challenging. So some optimization might work, some are not working. You have some gate fusion, some gate distribution reducing, but just to let you know, it's not easy. It's also from software development. And what I want to show you is that the project I mentioned to you, the Intel Quantum SDK, is provided as a Docker container for free, but we have also several open source projects. I mean, of course, the compiler is our IP, we cannot release. We have a special agreement with customer researchers that want to use the compiler. But we provided, for example, the simulator itself. The state vector simulator with noise is provided as an open source project. This is actually showing you some run that we did recently with on LRZ in 2020. So how scalable is the Intel Quantum SDK? Because this state vector simulator is MPI plus OpenOP ready, so you can write your application and scale on top of HPC system. What are other features that we have in Quantum SDK? Well, it's a C++ based programming, but they said, but I don't want C++. Maybe can you read Kazam code? Yes, I mean you can take your Kazam code, and then read and run on the simulation. What's the problem here? Kazam code doesn't read how you are going to write a hybrid algorithm. How you are going to simulate a hybrid algorithm if you only give the open Kazam code. It's better you have a single file where everything is written rather than giving a single Kazam code and let it run. You have to think about all this problem. And we provide a Python interface. The Python interface, it's very similar to others. You just have to set up and load some library. But those are the latest features that we have implemented, and also we have some kernel module already written. So we have an open source project with some written algorithms so that one can use. I still have time, right? Okay, good. Now, how to use this SDK? First, think about one thing I want to mention. This Intel Quantum SDK has been born to fulfill one point: to help our hardware researcher to test what they are doing. Okay? So then later we have seen that this is a useful software. It's a piece of software the community would like to have, and then we decided to make it public. But think about the fulfillment. That's why from time to time, for beginners, it's not easy. But this is the way. The software you are using is the software that our research is using to give feedback to the spin silicon. Okay. How do I get it? So there is a website, there is also at the end a QR code you can scan, you can go to the Quantum SDK page, and it's a simple Docker pull container, and then you are fine. So you are in a virtual environment where you can run your container. If you don't want to host yourself, we have the possibility to do through the cloud, but there are pros and cons on that. So maybe, it's just a suggestion. You could do this. You could do this as well. And then on this page, there are links about community and documentations, tutorials, and so on. Good. So what are the steps? Let me go here. So we, for using Quantum SDK, we think about four steps. So the development, this is your work. Writing your quantum workload. Then you have to configure the backend. Configure the backend. In this case, I show you the full state simulator, but you can configure another state vector simulator, or you can use the quantum.simulator if you like. Quantum.simulator is already configured like is behaving the spin silicon we produce, or you can give your configuration file if you're producing something different. Compiling, then generate the binary. It doesn't generate only the binary. Actually, the output is a bit more verbose. We generate intermediate representation and also custom code. So you're gonna see the compiler, which instruction does. And if you play around, I want to, if you come later, I can show you also on my laptop, but compiling. There are also compiler flag, optimization flag. And I can tell you that it's also nice to see when you change the optimization, how we have optimized the CASM. How the instruction is being released after the optimization. And then you run the executable. So running the executable is also a challenge, but let me explain. So first, it's a kernel-based programming. Think about accelerated compute, you have to write your kernel. What are the data types? We have introduced data types like a qubit register, a classical register that will allow you to store the data. So for writing the workload, we support all the known quantum gates. Support in the language. Supporting in the hardware is another thing. Is what the compiler knows, so also the configuration knows. Actually, you can prepare the state, the Hartman, then do the measurement C0, but it doesn't mean that this will be translated as C0 once you run on the spin qubit simulator. Okay? This is a snippet of code, so you see we have on the include, I think maybe with a pointer, just, so on simple like you include extension to the language and the quantum runtime, and then this quantum underscore kernel allows you to write everything related to quantum. So here is the main file. So when you write the main file, of course you can mix whatever data type here with classical, with some restriction, of course, but you can write anything classical here that will interact with the quantum hardware, with the quantum kernel. So actually the hybridization, the hybrid algorithm is already in the language. You can even use STL data type, vector data type. So there is a lot of variety you can have, so flexibility. Then the second is, before you run, you have to configure the backend. In this case, in this example, we are setting the quantum dots, the full state simulator. This full state simulator is the one that is the same that we provided as an open source project. But if you pull the Docker container, it's actually using the one. You don't need to download. Let's put it this: you don't need to download the GitHub project to get the simulator. Once you pull the container of the Intel Quantum SDK, you get the simulator. You just need to configure properly. And another thing is this full state simulator. Once you write, then when you compile, you have a binary. You can run with MPI. So it means that you can do MPI run, then the number of tasks and the binary, and then on the back end, the full state simulator will run on top of MPI. It means this is really already HPC ready. So compiling. So how do we compile? So we run this Intel Quantum compiler and then optional flex. This is still under development in the sense that we only have very few flex now, but things are moving forward. Every release, every quarter, we have different supported compiler flex. So if you want to know, all the compiler flex are with that, but those are the ones that we will support now. I mean, the standard -C -O or -I -L. This is what I'm saying, right? You can include external library. This is nice. I mean, you can include standard external library like BLAS, Lava. Of course, BLAS and Lava are working on classical part, but you never know. Maybe you get the results from Quantum and then you don't know, you want to do something on BLAS. And those are the optimization, O1, O0, O1. Those are the two steps. If you remember, the compiler can have optimization up to, I don't know, O3, O4 from time to time. But those are the quantum optimization. Okay. O0, it takes the data and then does whatever it does. And then O1 tries to optimize using some fusion of the gates and data techniques. You can also print out the circuit representation in tag form and so on, but this is also for maybe, because C++, I mean, what is the caveat here? If you are doing Python, the visualization comes kind of for free, okay? I mean, you can use matplotlib, you can have this graph with circuit. But here, use C++, everything is abstract, but I want to know those. I want to have the draw of the circuit, so we provide this as a tag file. So you just -p, and there is the circuit representation. So you can put in your paper, I don't know, it's a tag. We find very useful. The optimization level, so as I mentioned, this is O0, and then at the moment we have prototype rotation as the first optimization. And then running. So this is the, I'm not steps like this. So as I said, when you compile, you can in classical code, you have a binary. You can have some options, you can produce, I don't know, some assembly and so on. But in this case, automatically when you compile, you get two additional files. The intermediate representation and the human readable assembly for the Intel Quantum backend. Why we have that? Because our research is using to see if I change, I don't know, some line or change the order, how this will affect the simulation or how will affect the run on the hardware. This is very useful. So you can learn a lot. If you, I don't know, you think, okay, I don't want to use this Pauli optimization. I'm producing, I want to have an additional optimization. How do I know if it's doing the right thing? Then I can use the intermediate representation or the assembly to understand how it works. And then running is just simple as run, but we can have also, as I mentioned, an API run of this executable. And then with that, I think I mentioned everything I wanted to mention to you. Here, I mean, this is a QR code of the developer community, and this work actually would not be possible without the help of these two gentlemen. Please take the reference. So these are the quantum experts and quantum engineers that they work with me, Kevin and John. And I'm here to take your question. Thank you.